All right, calculus students, welcome to week 3 of our review process here. We're closing in on that AP test, which is going to be on, I think it was March 12th, if that's a Tuesday, sometime like 11 a.m. or something like that. Make sure you guys are checking that stuff out on College Board. We found out this week that we don't really need calculators anymore. I'm trying to gear most of the practice questions I give you then to be questions that you would not use a calculator for. But anyway, we'll go ahead and begin here. So once again, I've made a example FRQ that models the one that you guys are required to do this week. But let's go ahead and begin and see what we can do here. So part A says, the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. I guess in this formula down here, 100 would represent its adult weight, B would represent its current weight, and the difference between those being multiplied by a constant gives you the rate of change of that adult baby bird. At time t equals 0, when the bird is first weighed, its weight is 20 grams. If B of t is the weight of the bird in grams at time t days after it's first weighed, then we have this expression here. Something I'd like to draw you guys' attention to is that it talks about this function b of t, and you'll look down here in this differential equation. Notice there's no t in here. That's not common. Usually there's a t somewhere, but what it does have in there is it's got the b. So this b of t is b here. They just didn't put the parentheses t. And that's actually one of the trickier parts about this type of question. If you wanted to think of these things as x's and y's, it would be like the b is the y value, the t is the x value, and our differential equation only has a y in it. So that's a little bit tricky. Kind of got to watch out for that. So there are no t's in this differential equation. They're all b's. Let's go ahead and continue reading on here to do the problem. But basically this dB/dt, that represents how fast the weight of the bird is changing over time. And this is the formula you can use to predict bird's weight at any given time. All right, write an equation of the line tangent to the graph of B at t equals 0. Use your tangent line to approximate the weight of the bird when t equals 5 days. All right, so before I begin solving it, let's just review something. This is a graph of some kind. Let's just say it looks like that, okay? And what they want us to do is to write the equation of a tangent line at t equals 0. So I'm going to draw an x and y axis. I'll call that the t, and we'll call that the b. And let's say that right here is, t equals 0, right? So that would be right here on our graph. And if I were to draw a tangent line, it would look something like that, right? Now, they want to know what's the equation of that tangent line. So that's one thing that we have to do, is we have to find the equation of the tangent line. Next, it says we're going to use that tangent line, which, by the way, a tangent line's equation should look something like this, right? We're going to use that equation to estimate what the actual weight of the bird is at t equals 5. So something we talked about a little while ago was how tangent lines are pretty close to the original function. Like, the closer you are to the place where it touches, the more the orange line is kind of like the black line. In other words, the more the tangent line is like the actual function b. The black line represents the function b in this case, right? So the closer we are to the point of tangency, the more the tangent line is a lot like the original function. And the farther away from the orange line you get, the less similar they are. Well, let's just say t equals 5 is like right here. Okay, well that would put me a dot right here. And as you can see, the orange line can give you an estimate that's pretty close to the black line. Those two dots are pretty close to each other. And so that's what they want us to do, is they want us to find the equation of this tangent line and then use that tangent line to estimate what the value of the b function is at that point. So we call that a linear approximation. Vocabulary you may be expected to remember. All right, So let's go ahead and begin here. Now, how do you find the equation of a tangent line? Well, you need three things. You need an x, you need a y, and then you need a slope. Now, in this problem, the x and y are, as I said before, b is kind of like your y, and x is kind of like your t. Now, you don't have to write that if you don't want to, but if you write stuff like this on your FRQ, you're going to need to define what those things are. So if you wanted to be more careful and write less, you could just do this instead, right? So x is like t, b is like y, and my slope is the derivative of b, right? So I'm just going to eliminate all those now that we've got those things defined. Oops, didn't want that. Okay. Well, they gave us a t value, right? The t value that they gave us in question 1 is t equals 0. The next thing is we need a y value to go with that. Now, it says at the beginning, when the bird is first weighed at time t equals 0, the bird's weight is 20 grams. The next thing we need to do is we need to find b prime of t. Now, another way of writing b prime of t is db dt. We have an equation for db dt. So what we're going to do is we're going to plug in the values that they gave us. Now, the only thing we need to plug in is a b value. Like I said, the strange thing about this expression is it only has a b. It doesn't have a t in there. So we're going to plug in the 20 that they gave us to figure out what the slope is at that point. We end up with 16 there. So I've got my t value, which is kind of like my x. I've got my b value, which is kind of like my y. And I have my slope, which is 16. Okay? That's enough information to write a tangent line equation. Forgot, that's how you can find the equation of a tangent line. You're going to put the b value, the y value that they gave you in, which in this case is 20, or b value or y value that they gave us. Slope that we found was 16, and then we're going to plug in the t value or the x value that they gave us, which is 0. And then we're going to go ahead and we're going to simplify this. So if I ever distribute this 16 in, I get 16 in x, and that's just going to be 0. And then I'll add the 20 over. We get that. So that's the first part of my question there, is finding the equation of the tangent line. And for that, they're going to give you probably 1 point for just finding the equation of the tangent line. And the next thing we're going to do is we're going to use that tangent line to approximate the weight of the bird at t equals 5 days. Okay. Now remember, we're going to say that x is playing the role of t here. So y is equal to 16 times 5 plus 20. And if we do that, I end up with y equals 100. Okay, so that's what we would say that the weight of the bird is at 5 days. I don't like this answer because that means it only took the baby bird 5 days to become a full-sized bird, which is obviously unrealistic, but I guess we're going to ignore realism here and we're just going to go with what we got as an answer. There you have it. So that's how you can find a tangent line and use a tangent line to approximate the weight of the bird at t equals 5. Now the next thing it's asking us to do is to find the second derivative and determine the concavity on the interval from 0 to 100. Oh, and by the way, on the last question here, you would get a second point for getting the correct estimation. So I would say that's a 2-point problem. All right. Anyway, back to question 2. We want to find the second derivative, and we're going to find out what the concavity of our function is on that interval. Okay. All right, well, how do you find a second derivative? Well, here's my first derivative. So to find the second derivative, we just have to take the derivative of that. But before we do that, I'm going to simplify this expression here a little bit. So say that dB dt is equal to 1/5 times 100 is 20, and that can become 1/5 b. Now, like I said, we want to take the derivative of the first derivative in order to find our second derivative. So we're going to take the derivative of this whole expression. If I take the derivative of that with respect to t, I end up with d squared b over dt squared. And then next, if I take the derivative of 20, that's just going to become 0, so it goes away. Now this one's kind of wild here, so pay attention. So usually if you take the derivative of something with a letter, just a single letter to the first power, right, all you get is that constant left over. But also remember that anytime this bottom variable is not matching this, that's a chain rule. That's implicit differentiation. And so when we take the derivative of this piece here, the constant rule keeps that 1/5 there, but we also end up multiplying by a factor of b. Okay? So there's that. Now, to take it one extra step, a little bit. Erased one, I'll put that back. Okay, well, that little piece there that comes from taking the derivative of b, we actually have an expression for that already, don't we? dB dt is that circled part. So here's how we'll write our final answer for that. I'm going to replace this dB dt with what dB dt equals, which is 1/5 100 minus b. Kind of weird. We can actually simplify that a little bit more. We can multiply those 1/5s together, right? And get negative 1/25. If you wanted to, you could even distribute it in, but I think I'll leave it like that for now. But there's my second derivative, so that there is going to be worth 1 point. Okay. Now the next thing it says, determine the concavity of this function on the interval from 0 to 100. Now, you guys notice something here, that this is negative, right? Well, actually, before I get into that, how do we know concavity? Well, we talked about concavity a little while ago. When f double prime is less than 0, your graph will be concave down. And when f double prime is greater than 0, it's concave up. Okay, so we're going to use this second derivative here to figure out whether this function is concave down or concave up on the interval from 0 to 100. Well, think of any number that you might choose between 0 and 100. So it's got to be less than 100, right? But greater than 0. So no matter what number you plug in here for b, like let's say you plugged in 50, right? You're going to get 50. And 50 times negative 125 is going to be negative 2. And so you end up with a negative number, right? And no matter what number you pick between 0 and 100, since b is always going to be less than 100, this one's always going to come out positive. And this one, since it's a constant, will always be negative. And a negative times a positive will always be negative, and therefore our graph will always be concave down on that interval. Okay, so here's how we would write our answer. Clear up my board here a little bit. So since d squared b over dt squared is less than 0 for all b between 0 and 100, the graph would be concave down. The graph of b would be concave down. So that's how you'd write your answer. Okay. And that little explanation there would be worth a second point. So once again, 2 points. So for question 2, 1 point for finding the second derivative, and 1 point for telling me what the concavity is with an explanation. Okay. Let's go ahead and move on to number 3. Determine whether your estimate in number 1 was an underestimate or overestimate. Justify your answer. Justify your answer using your answer to part 2. So they want to know, was our tangent line approximation from part 1 an overestimate or an underestimate? Well, when you have a concave up graph, a tangent line will always be an underestimate because it's under the curve. If you have a concave down graph, your tangent line will always be an overestimate. So our answer up here was that at t equals 5 days, the bird's weight would be 100 pounds, right? That was our estimate. Our answer to number 2 was that our graph is concave down. So determine whether our estimate number 1 was an underestimate or overestimate. Well, our graph was concave down, so our tangent line would give us an overestimate of the actual value. So 100 pounds is actually a little bit more than what the bird would actually weigh at 5 days. So how would we write our answer? Here's how you would write it. You would put, since B is concave down, for all B in between 0 and 100, our estimate of 100 pounds in part 1 is an overestimate. Since B is concave down, for all values of B between 0 and 100, our estimate of 100 pounds in part 1 is an overestimate. Okay? And that's a 1-pointer question right there. Let's go ahead and move on to number 4. Now, number 4 is very algebra-heavy stuff. So let's be ready for it. All right. So we want to find a particular solution with our initial condition that's been provided. Okay, initial means that they're going to give you a specific t value and b value. Okay, and in this case, what they gave us, let me back up a little bit. The t value they gave me was 0, and the b value that went with it was 20. So that's my initial condition. I'm going to use that to get what's called a particular solution. Now, a particular solution to a differential equation is we're looking for what was the original function. That's the question. What was the function? If this is the derivative, what's the original function? Okay, and you do need the initial condition to help you find something along the way. So question 1 is, how do you get from a derivative to an original function? Well, the answer is you integrate. But when it's an implicit function, and in other words, when your y is on the other side, you have to get the y and the dy together and the x and the dx together. You have to separate the variables. Okay? And then you integrate. And after you integrate, you're going to get a c value, and that's what the initial condition's for. It helps you find out what the c value is. Okay, so let's go ahead and begin. So here's our problem. The first thing you're going to do is you're going to separate the variables. I want all the b's on one side, and I want t's on the other. Now, to do that, what we're going to do is we're going to divide both sides by 100 minus b. So now I got both of the b's on the same side there. I've got 1 over 100 minus b db dt, and 1/5 over here. But I don't want this dt here, so I need to get rid of that. I'm going to multiply both sides by dt. That cancels. And whatever you do to one side, you do to the other, right? And so now we have this. So we've separated the variables. And you don't have to be as detailed in your work as I'm being. You probably literally could have gone from here to here without showing any work, and that would be fine. But just so you guys know, usually on these exams, just doing that is worth 1 point. Just so you guys know, these types of questions, they're hard and they're a pain in the butt. But, where was I? But they're very much worth your time to figure out because they're worth a ton of points. And that's your first point, okay? Now, the next thing we're going to do is we're going to integrate both sides. Usually on these problems, you get 1 point for integrating each side, not just showing the symbol, but actually doing the integration. Now, on the right side, that's pretty easy. Anytime you have just a number here, you just put that letter next to it. So we have 1/5 t. Don't forget your plus c, right? This other side, though, is a little bit harder. Don't like how I started. This side over here is a little bit harder. How do we integrate this type of expression? Well, hopefully you guys are a little bit sharpened up on your integration, because we did some integration review last week, was it? Was that 2 weeks ago? I can't remember now. 2 weeks, I think. All right. So how do we do that integral on the left? Well, the answer is it's a u sub problem, and it's going to turn into an ln. So what I'm going to do is I'm going to let the u be the bottom piece here. So I'm going to say that u equals 100 minus b. I'm going to find the derivative of u with respect to b, which would be -1. Now notice this time when I take the derivative of b, I don't get a b prime because this matches the thing I'm taking the derivative with respect to, so it's just -1. Multiply both sides by db, and then divide both sides by -1. And we find out that db is a negative du. So now we're going to rewrite this expression here on the left in the following way. This is going to become a u, so now it's 1 over u. I'm going to replace db with du, and it had a negative in front of it, right? So I'm going to put that negative in the front. Okay, oops, didn't want to do that. Step up a little bit. We're making some good headway here. All right, next thing we need to do is we need to actually integrate this. So the integral of this is ln of u. Don't forget that negative in the front, though. Okay. Now, once again, you can't leave the u there. You have to replace it with what u equals. U was 100 minus b. Now, by the time you get to this point, you've racked up 3 points. So the first point was just separating the variables. The next 2 points are integrating each side of this equation. So this side over here, if you got that correct, would be a point, and this side over here would be a point. So that's 3 points now total. Right? Now the next thing that we're going to do is we're going to, let's see, plug in our initial conditions so we can find the C. Okay? So we have negative ln, absolute value of 100. Now the B value that they give me is 20. And the T value they give me is 0. So this is gone, and I have ln of 80 here. And there's my C value. Pretty simple. All right. So that there would be worth another point. So we're up to 4 points now. That's almost as much as the other 3 questions combined. Matter of fact, by the end of it, this thing will be worth just as many points as the other ones combined. So number 4 is a very important type of question. I included lots of these also in your multiple choice for this week as well. Just really want to make sure you guys got this down. All right. So there's that. So now we have a particular solution, but believe it or not, we're still not done. I'll tell you why we're not done. But here's my particular solution. Now the reason why I'm not done is because they want us to find a particular solution, and that means they want the b by itself. Usually when you have a function, the answer shouldn't be written in implicit form. If they want you to write a function b of t, then usually what they want you to do is to go ahead and find the original b value. Oh, I made a boo-boo though. I forgot to include my the C value that I found. So we found out that C was negative ln of 80, right? All right. Now, what do? We want to get the B by itself. So the first thing I'm going to do is I'm going to multiply both sides by a negative to cancel out the negative on the left side. All right, so that just changes the signs of everything. Next thing that we're going to do now is we want to get rid of that ln. The way that you get rid of the ln is by exponentiating both sides. Looks like this. And this e cancels that ln, and we're left with this now. Almost there. Now, just so you guys know, the function e, it doesn't matter what its exponent is. You don't need to draw this on your solution, but the function e, no matter what its power is, will always look like that, or it'll look like this. It's never going to go down here where the y values are negative. Okay, so my point in telling you that is so that you guys will understand what I'm about ready to do next. Since this side here is never negative, then the absolute value bars over here don't matter, because this side's always positive anyway. Okay, but we had those absolute value bars there because that's how you take the integral of ln, right? Or I mean 1 over u. Anyway, now you could probably leave this side like this and that would be fine. However, I want to show you guys how to write it the way that they usually will write it. But if you just left yours like that, on the right side, that'd be fine. We still got to move the 100, but I'm going to ignore that for a minute. I want to show you guys how they would usually write this. We can rewrite this expression like this. anytime you have two exponents being added together, that's because you had two that were being multiplied to begin with, right? When you're multiplying two terms that have the same base, you add their exponents, right? So we're just kind of like working backwards, separating. Why would I do that? Because now the e cancels the ln, and I'm left with an 80. And so you actually end up with a much prettier looking answer if you do that. I'm going to rewrite it just with the 80s in the front. That's how it would normally look. There we go. The last thing that we need to do is we want to get the 100. We want to get the b by itself, basically. So I'm going to subtract the. You could do it however you want. I think what I'm going to do is I'm going to move the b to the other side and then move the e to the other side. So if you were to add b on both sides, you would get the following. And then if you were to subtract the 80e to the negative 150 power, you would finally have the b by itself, and that would look like this. Oops. A little boo-boo there. Hold on a second. And there you go. So there's our final point, which takes us up to a grand total of what now? I think it's like 4 or 5 points altogether. So we had 1 point for separating variables, 1 point for integrating both sides, that's a total of 3, 1 point for plugging in your initial condition to find c, and then 1 point for getting the b by itself. That's 5 points altogether. That's the same amount of points you would have gotten for just doing 1, 2, and 3. And it's a very common type of question on differential equation questions. I can almost guarantee you guys are going to see one of these. And remember, you've got a 45-minute test, which means you're only going to have 15 questions. And this guy here is going to rack up a ton of points. I would invest some time in that. Now, I could be wrong. It's very possible they don't even have that question. However, I will say every year on every FRQ, they always have that question, and it's worth a lot of points. So, I don't know, because of the pandemic, maybe it's different this year, but I would expect that to be there, and it's certainly worth your time. So I put a lot of practice problems like this as well on your guys' multiple choice this week, and I'd really spend some time on that. Anyway, let's get back to the rest of the FRQ here. The next one here says, sketch the solution curve provided that b of 5 equals 70. So this is what's called a slope field, okay? And we learned how to find slope fields a little while back. You plug in any coordinates you want, like 570 over 5 up 70. So that's going to be like what? Like right about here, right? Now you plug in that point into here, and it will tell you the slope. And you guys can see those little lines right there. That tells you what the slope is at that point. But instead of asking us to sketch the slope field, because they've already done that for us, they're asking us to sketch the solution curve. In other words, they want us to show what does the b function look like. We just found it. The b function was something like this, right? They want us to sketch what that function looks like in the slope field, but it's easier than that. You don't even need that to get the answer. How I taught this when we did it in class was, think about the slope field here as kind of like the currents of a river, and that dot that's there as a twig that you dropped into the river. Which way would that twig flow if it followed the current? Well, here it's going to go like this until it comes up here, and then down here it's going to like kind of do one of these numbers like that. So it's going something like this. Okay, that's really messy, but hopefully you guys got the idea. Maybe I can make it prettier. Let's see. So we had a dot here, like that. Nope. It's hard to do this on my computer. They probably won't ask you to do one like this on your computer screens because of the format of the test this year. But what they could do is they could give you I don't know, maybe I don't know what they could do. Maybe you won't even see a question like this. I don't know. But very common question usually, so I included it, but I don't know what creative thing they'll do this year. I don't know how they would do that without multiple choice if they're not going to actually use pen and paper. But anyway, just to be ready, we'll cover it. All right, now we're going to move on to part B. Determine if the piecewise function is differentiable for all values of x. All right. How do you tell if a function is differentiable? I don't like writing very much. All right, so the first thing that you're going to do is you're going to check if it's continuous. Function cannot be differentiable if it's not continuous. Now, how can you tell if a function is continuous? We talked about that last week, I believe. First, the function has to exist. Second, having some technical difficulties here. Okay. Second, the limit must exist. And then third, the limit at c must equal the function at c. We talked about that last week. But that's just for continuity, and that is required for differentiability, but we also have to check to see if the derivative exists. And this one, I'll write it by hand. Does just a second, having a little bit of a technical difficulty here. Okay. So does the limit of the derivative at c as x approaches c from the left equal the derivative of your function as x approaches c from the right. Okay, so the limit from the left and right have to be the same. The slope has to be the same. Now, when you guys do your multiple choice this week, you're going to do it graphically in some parts, so that's actually a little bit easier. But an example of where this would not happen is a cusp. If you have a cusp, the slope on the left is not the same as the slope on the right at that cusp. On a smooth curve, it is. The slope on the left is approaching 0, and the slope on the right is approaching 0. So that, a smooth curve, the derivative does exist because the limit of the slope as x approaches c on the left is the same as the limit as x approaches c on the right. But cusps are no good. So that's how you can tell if a function is differentiable or not at a given point. So we're going to go ahead and apply that principle here. See what we can get. All right, so let's begin to check and see if our function here is continuous. Now, first of all, cosine and a linear piece here, those are both continuous everywhere. They never have any holes, gaps, or jumps. Square root functions are continuous everywhere as well, so long as you're not somewhere behind the 0 here. So we're good to go. All right, so let's go ahead and establish if they are connected first. In other words, is it continuous? So to do that, we're going to see, is the limit as x approaches 0 from the left of my function equal to, I'm going to put a question mark because we're not sure if it is yet, is it equal to the limit as x approaches 0 from the right? Now notice it's not the derivative right now, right? I'm just doing continuity. I'm not doing differentiability yet. I'm going to start with continuity. We'll do differentiability last. So if I'm approaching 0 from the left, I'm going to use the top piece. Six cosine x plus 3x. And if I'm approaching 0 from the right, I'm going to use the bottom piece, which is 6 square root of x plus 1. Now direct substitution, cosine of 0 is 1, and 1 times 6 is 6. So I have 6 here, and if I plug in 0, I get 0 at this point. So 6 plus 0 gives me 6 on the left. Let's do the right side. If I plug in 0 over here, I get 0 plus 1, which is 1, and the square root of 1 is 1, and 1 times 6 is 6, and so boom, we have the limit from the left and right are the same, therefore it is continuous. Now, let's just say they didn't come out equal. At this point, if they didn't come out equal, you would say the function is not differentiable because the function is not continuous. But in this case, since it is continuous, we're going to press on. We can't say it's differentiable yet, but it's looking good so far. Let's go ahead and do the next part of our test here. The next part of our test is we want to do the same thing, but this time we want to see is the slope from the left the same thing as the slope from the right. Okay. Oh, one of these is backwards, by the way. Probably should have been this one. Needs to be pointing that way. I didn't notice that till just now. Anyway. So, we need to find f prime before we can answer this question. And the way you find f prime, basically, is just by taking the derivative of the top and the derivative of the bottom. So let's do that. So the derivative of the top, the 6 is going to stay there. The derivative of cosine is negative sine. So now it's negative 6 sine x plus the derivative of 3x is 3. Next, we need to find the derivative of this. The 6 is just going to stay there. And when you take the derivative of a square root, you always get 1 over 2, and that square root stays the same. You also need to multiply this by the derivative of the inside of the square root, which in this case is just 1. Now, if I were to simplify all this, 6 times 1 on the top is 6, divided by 2 is 3. So I'm going to go ahead and just simplify this now to save space. But if you multiplied all those together, you would end up with this as your final outcome. And so here's our derivative of f. Now, we're actually not sure if x can equal 0 yet. We're not sure. Because if the derivative doesn't exist at 0, then we can't put it equals 0. It can't have a derivative at 0. But that's what we're going to test over here. So let's see if it actually does work out. So if I'm approaching 0 from the left, then I'm going to use the derivative on the top. Question mark there because we're not sure if they're equal yet or not. And if I'm going to find the derivative from the right, or find this limit of the derivative from the right, we're going to use the bottom piece, which is that. Now we'll just go ahead and do our direct substitution here. Plugging in 0 to sine makes 0, so that's 3. Plugging in 0 here, you get 3 also. So the slope is also the same on the left and right. And so we would say, yes, the function is differentiable at x equals 0. Now, on your guys' question, I don't know if you guys have what I have here, but I'm going to switch gears a little bit. So both of these functions are continuous everywhere, but one of them is not differentiable everywhere. This one is differentiable everywhere because it's a sine function. Sine functions look like a wave and they never have any holes, gaps, or jumps. This guy has a discontinuity. Do you guys see where it would be? It has a discontinuity at x equals -1. So even though this piece connects, the top piece of our function connects to our bottom piece, and so here's our top piece, and here's our, I'll change colors here. Here's my bottom piece. They connect, and they even connect at a smooth point. The problem is that for this function here, it's not differentiable when x equals -1, but that's actually okay. Do you guys know why? Because this bottom piece only applies where x is greater than 0. Since the discontinuity isn't on that interval, then we're okay. Right? So that's kind of a small technicality. But up here at the question, it's asking us, is this thing differentiable for all values of x? Well, this function here is continuous and differentiable everywhere. This one is continuous, but it's differentiable. It's not differentiable when x equals -1, but that's not on this interval anyway. Furthermore, the top piece connects to the bottom piece at a smooth curve, and that's what we've been showing over here all this time. And so, to answer our question, we would say yes, the function is differentiable everywhere. So for this part, I just put all this work we showed just shows us that the function is differentiable at x equals 0. But since this discontinuity is not on the interval, we can say, yes, the function is actually differentiable everywhere. Now, I don't know if you guys are going to run into that on your problem or not. You may. But the point here is usually you're just checking to see is it differentiable at where they connect. But I digress. Let's go ahead and move on to our last question. I don't know if you guys will see a related rate question on your FRQ this year. It's very possible, but I don't know for sure. The issue with a lot of these is that sometimes a lot of the ones I gave you required a calculator, but I have seen a lot of related rate questions on the FRQ that don't use calculators. So, hit or miss, we'll see what happens. I included a lot of these also on your multiple choice for the week. So let's go ahead and begin here. Now, a little while back, I gave you guys some steps for finding whether or not a function, or finding the related rates of a problem. I put the steps over here for you guys. You have them in your notes already. But the first thing we're going to do is we're going to draw and label. So let's read it. It says an observer stands 300 feet away from a launch pad. So if I have my launch pad here, my observer here, the distance between them would be 300. The rocket blasts off and maintains a velocity of this. Now that's dA dt. That means the height is represented by the variable a, and it's moving up at this particular speed where t is in time and a is in feet. They want to know how fast is the distance between the observer and the rocket changing when t equals 4. What segment would represent the distance from our observer and the rocket? That would be a line here. What should we call that? We'll call it C, I guess. Right? Now, usually in these problems, not always, but usually, one of the numbers that they give you will be a constant. It just won't be changing. But for the things that are changing, we like to put letters there because they're changing, not always the same. But if on your picture for things that are actually fixed and unchanging, I would go ahead and label that. All right. The question is asking us, how fast is the distance between the observer and the rocket changing when t equals 4? All right, so part 1 is done. We've drawn and we've labeled our picture. Identify the given rate. Here is our given rate. Wherever you see velocity, rate, or dA over dt or something like that, that's a velocity. So there's my given rate. And that's in feet per minute. I want to pay attention to our units. We also want to identify our desired rate. How fast is the distance between the observer and the rocket changing? That's our desired rate. And that's how fast c is changing. So the way that you would write that is dc dt. And that's going to be in feet per minute as well. Now, as long as that rocket's going up, we would expect the distance to be increasing. In other words, we would expect the rate of change to be a positive answer. Okay? You have to remember to sometimes put negatives in if it's something's decreasing or something like that. All right. Now we want to create an equation that relates the two variables. What two variables? Well, here's the rate that I know, the rate of A. I want to find the rate of C. So I need an equation that's going to relate this variable to this variable. And hopefully you guys are thinking of good old Pythagorean Theorem. So step 4 would be A squared plus B squared equals C squared. Now I've got an equation that relates the A to the C. The next thing we're going to do is we're going to differentiate our equation. Now, this is a part you got to remember. When you take the derivative of this, we're taking the derivative of it with respect to t. Everything is with respect to t, in case you didn't notice the little dt down here on the bottom. Let me clean it up. See the little dt down there on the bottom? Everything is going to be with respect to time when you're doing these related rate questions. Okay, so let's go ahead and take the derivative. So the derivative of a squared is going to be 2a, but times dt, right? Anytime you take the derivative of a letter that's different from the bottom, then you multiply it by a prime factor, or in this case, instead of putting a prime, I'm going to put d/dt. Plus, the derivative of a constant is 0, so that just goes away. And then the derivative of this is going to be 2c dc dt. Now, number 6 is where we kind of are going to separate the algebra big boys from the algebra little boys. Can you find everything you need and plug stuff in? So what am I trying to find? I'm trying to find dc dt, right? I want to find this, which means I need to know what c is. I need to know what dA/dt is, and I need to know what a is. Now I just realized that I left out a piece of information that was needed on this problem when I made it. I didn't have this before, so I just added it in case you didn't notice. But let's go ahead and finish the problem. So in this problem, I know what A is because I just put it there. Oh, I cheated. Next thing is we can actually find this. How can we find dA/dt? Well, we know that t equals 4. So if you plug in 4 for t here, you can find dA/dt. Let me write these numbers here. So we're going to plug in 72 for A. Let's go ahead and figure out what dA/dt is now. We're going to find dA/dt by plugging 4 into this equation here. That's going to be negative 72 and 216. Let me use my calculator here. 144. So we end up with 144 there. So I've got 144 for t, and the last thing we need to find is c. How can we find c? Well, we know b is 300. We just found out that a is 72 at the point in time that we're interested in. We can find c by doing our Pythagorean theorem. That. So you just kind of have to go through and use whatever math you can to figure out all the missing pieces until you're ready to get that last piece in there. So we have a squared plus b squared equals c squared. And from here, I'm just going to use my calculator to save some time. And like I said, on your guys' actual worksheet, I tried to give you guys problems where you wouldn't need a calculator just because for the most part, they're just not going to be giving you calculator type questions. I mean, technically, you could do this without a calculator. It would just take forever. And we want to take the square root of that. Well, I don't end up with a nice number. 308.5 is what I get. I'm just going to round it to 308. Okay, so this is all getting pretty messy. I think I'm going to go ahead and clean things up a little bit here. And this is what it would look like if we were to plug everything in with our A, our dAdt, and our C here. And I rounded that like I said before. Now we're going to go ahead and calculate those out real quick. And this is what we would get by multiplying the numbers together. And then finally we want to solve for what we're trying to find here, the dCdt. So what I'll be doing next is I'll be dividing both sides by the 616. And since this is an FRQ and we're not using calculators anyway, I would encourage you guys to not do basic math. It's unnecessary, especially since this is our stopping point. However, since I have a computer, I'm going to go ahead and do it anyway. 20,736 divided by 616 is 33. And we're just going to round it. I'm being really kind of ghetto with this just because you guys aren't going to have questions like this on your FRQs anyway, just because of the fact that you're not using calculators. But technically, we talked about how you always round to the third decimal place, or the third number after the decimal place, right? But anyway, there you guys have it. So that's how you do it. A 7-step process, and you don't want to forget your units is the last step, and that's in feet per minute. Okay, there you guys have it. So that's your FRQ help.